Now, this week we're going to deal with dual simplex algorithm. It's actually, it will remind you of the duality because of its name, but it's a different entity, different algorithm completely. It's something we use most frequently instead of big M or two-phase or any other method, because it is used to deal with non-positive or negative right-hand sides all the time. Now, we don't have to use, of course, we can have negative right-hand side on the objective function, but when this is, constraint, we are trying to see if we can get rid of negative right-hand side values. And dual simplex helps us with that one. Now, yeah. Now, what we use dual simplex for? For example, finding the optimal solution, new optimal solution, after adding a constraint to the LP. Now, when you add a constraint to an LP, that LP might lose its objective, optimality. Why? Because the new constraints might be more, constricting, and it might be limiting your feasible region. Your feasible region might be getting smaller because of the new constraint, and you might be losing your optimal point. Remember that point? We had drawn lots of maps like this, for example. We said that there are 1, 2, 3, and 4, of course, it's origin, 5 points that can be optimal if this is your feasible region. So these 5 points can be optimal points. Of course, we can have alternatives between them, alternative solutions, but still, among these 5 points, if, for example, this was your optimal solution, and you introduced a new constraint, something like this.
Hocam, tahta biraz bulanık gözüküyor ama.
Zoom yaparsa daha iyi olacaktır diye umut ediyorum. Bakalım, bilmiyorum. But you can understand the, concept. There's an optimal solution point over here in one of the, corners of the feasible region. And then you add a new constraint that removes that optimal solution point completely. Okay, it negates it. It's destroyed, it's gone. So you have to find a new solution. And your new optimal points are like this, 1, 2, 3, 4. One of these 4 points is now your optimal solution, so you have to find it. So what you need to do is just start from here and do the simplex to get, for example, to here, then to here or here or here. Depends on what your objective function is telling you. But still, this optimal solution is gone. Okay, with the new constraint, you have lost this point. So you have to find a new point. This point still exists, but it's outside your feasible region. Okay, this point still exists. You are still at this solution. You have found the solution, you are at this solution, but this is outside your feasible region, so you cannot use it anymore. It's not feasible anymore. Okay, so what you need to do is just move a step closer to the feasible region from here, or maybe it will go from here and to here. It depends on the algorithm itself when you are, making iteration. It can go both ways. Okay, maybe it will just go 2 steps and say that this is the optimal solution. I'll just go from here to here and say this is the optimal solution. We don't know which point is the optimal solution, but we are just saying that any one of these can be the optimal solution. Now, dual simplex helps you with that. This is one of the things that it can do. Okay, with the constraint, with a new constraint, you are losing an optimal solution point, so you have to get back to a feasible area, the feasible region. Now, for example, you can change the right-hand side of an LP, the right-hand side of the constraint, and then your LP will change once again. For example, in the same solution, you may move one of your constraints up or down, okay, depending on how you change its right-hand side. And when you do that, the right-hand side moves, okay? It either goes up or down once again. Now, with that one, we can, once again, let me just get this mouse further back over here. So I can, yeah. Now, with that one, we have to once again change the right-hand side. If it's a negative right-hand side, we have to make an iteration on that right-hand side, on the negative value, and change the optimal solution once again, okay? And then the third one, the third one is for actually minimization problems, let's say most of the time, but it's about dealing with the greater than signs in your constraints. Now, in the third one, I'm pretty sure you remember, we used to use big M or two-phase, as seen in the midterm. And with two-phase or with big M, we would have to introduce artificial variables into the model. With dual simplex, we don't need artificial variables anymore. We can just use the variables we have at hand. Now we will see examples for all of them and more, hopefully. But still, the dual simplex is the same algorithm which can be used for any of these situations. Okay? It's all about seeing the right-hand side that is a negative value and dealing with it. Once again, this is for constraints only. Your objective function itself can have a negative value because there might be negative coefficients for your variables in the objective function. So we don't care about the sign of the objective function. It's all about the constraints all the time. So if we see a negative value on the constraint on the right-hand side, we will use dual simplex. Of course, there are some rules for that. We have to make sure that we can, apply dual simplex before we start trying to apply it. And those rules are: first of all, we have to make sure that the current solution looks optimal. That means that it conforms to, it checks out all optimal conditions. For example, if it's a maximization problem, there should be no negative values on the objective function row. They should all be 0 or positive. If it's a minimization, they should all be negative or positive. Negative or 0, no positives in there as well. So the first thing we have to check, which is the most important part for dual simplex, because you cannot apply dual simplex, is that the objective coefficients, objective function coefficients, conform to the optimal conditions. This is the most important part. If it's not happening, you have to keep making iterations, normal simplex iterations, till you get an objective, optimal objective function row. Then you can check right-hand side. For example, you have a model, you have a table, and in that table, in the simplex table, your right-hand side values are, some of them are negative, but you don't have an optimal objective function yet. Then you have to keep going with the normal simplex, to find the optimal objective function, to get rid of all negative values if you have a maximization problem in there. Then we have to choose the most negative right-hand side. If this is okay, if we have an optimal, objective function, if we say, okay, this is an optimal solution, but there's a negative right-hand side, which is normally infeasibility for us, but still there's a chance that it's not infeasible, which comes into effect with dual simplex. We have to find the most negative right-hand side, start with that one. Then we will just ratio test once again. You will see what I'm talking about. The ratio test is coefficient at row 0 over coefficient at pivot row. There's the fourth one, but still, we have to find which point we are going to pivot. And then we're going to find out who enters and who leaves the solution, just like normal simplex. Remember, with big M, with two-phase, they were all about finding the pivot point. So you could just apply normal simplex. This is the same. We're just trying to find the pivot point, the cell or the coefficient which will turn into 1, and let's apply normal simplex once again. Dual simplex is all about finding that pivot point starting from the negative value on the right hand side. That's it. It's pretty simple actually, but it just looks horrifying sometimes, but it's not. It's just about finding the pivot point, and then you apply normal simplex once again. It's all about normal simplex. Just finding that pivot point is what happens with all different types of simplex, up to now at least. So we said that the variable with the smallest absolute ratio, once again, the ratio should be the smallest one, enter the solution. So how do we do that? For example, let's start with a simple example. Now, this is a maximization problem, and it's an optimal solution for now, and we have zeros for x1 and x2 and s3. So x1, x2, and s3 are our optimal solution numbers, so they are the basic variables because they make up the identity matrix also. So s1 and s2, instead of x1, x2, and s3, s1 and s2 are non-basic variables, and they have coefficients of positive coefficients, so it's an optimal solution. But there's a right-hand side that is a negative value, minus 0.75. So normally we would just say that, okay, this is infeasible, it can't happen. But dual simplex said that, okay, this might be feasible. You might just be out of your, feasible solution, like this one. You might be over here, which would give you a negative slack value. So all you have to do is just come back. To do that, we have to find the ratios, starting with the right-hand side, the minus 0.75. Okay, when you start with minus 0.75 over here, you have to check the negative values inside, okay? The negative values in the table. Of course, you don't check the right-hand side values, just the coefficients for your constraints, variables in the constraints. So we have two negative values over here, which is minus 0.75 for S1 and minus 0.25 for S2. What I need to do is just find the ratios for these two values. So I will just divide 125 by 0.75 and 0.75 by 0.25, and I will get those two ratios, 166 and 3. The smallest ratio is 166, so the pivot column is S1, which means that S1 will enter the solution, and as the row belongs to S3, S3 will leave the solution. And all I need to do is just turn minus 75, that point, to 1. That's all. So if I can just switch that into 1 by doing a line operation, a row operation, and then get rid of all the values above it, turn them into 0, just as normal simplex, then I will have made an iteration. Okay? And this is what I do. I just turn minus 75 into 1, and then get rid of all the values above it, turn them all into zeros, doing the row operations we have been doing for now, up until now, and then this is it. We're done with it. So at this point, okay, it's still optimal solution because there are no negative values on the top side and no negative values on the right hand side. So we are done with it. Okay? As we have got rid of all the negative values on the right hand side and the negative values on the top side, we can just say, okay, this is optimal solution, we are feasible. Okay? Now, there's one important point we need to keep track of over here. As you can see in the previous table, the Z value was 41.25. Okay? But in the second table is 40. It's going down. It's a maximization and it's going down. Why? Simple. Because we are correcting a mistake. As I said, we were out of bounds. We were out of the feasible region. So we found a higher value for it. But when we correct our mistake and go back to the feasible region, our mistake gets corrected and our value gets smaller. Okay? So instead of 41.25, we get 40. Okay? Normally, with maximization, at each iteration, you have to increase your Z value, or you can just stay at the same value if it's an alternative solution or there is degeneracy, etc. But as long as you make an iteration, you are expecting to increase that value. With dual simplex, that value in a maximization problem might decrease, usually decreases, sometimes stays the same. It's very rare to see it increase, very, very rare, because you have a negative value over here, and you are trying to get rid of the negative value, and so you are just adding it upstairs if it's an addition. But for example, if S1 had a negative coefficient as well, well then you would say that, okay, this is not optimal and I have to correct this. So you cannot just subtract it. Okay? You keep adding the negative value to the top side. I hope you're keeping track with this, but still, if S1, the objective function coefficient of X1 was negative, then this wasn't an optimal solution anyway, and you have to make the normal iteration, normal simplex iteration anyway. So we usually lower our Z value when we make dual simplex for maximization. For minimization, this means the other way. This means we go the other way and we increase our Z or W value. Okay? So dual simplex is used to correct our mistakes most of the time. We can assume that this is a mistake, of course. We'll see. Now, what if we add a constraint? Now, this was just a simple, let's say, mistake or a simple, iteration, let's say, outcome, for example. But we can also add a new constraint. Now, as I said earlier, when we add a new constraint, this part, this optimal solution part, might now be out of our feasible region area. Now, when that happens, we have to just go back to our feasible region once again. Adding a constraint is the, let's say, hardest part, I would say, probably for applying dual simplex, because the other ones are pretty easy to understand, but adding a constraint part is a bit more difficult most of the time, but still, it's not that hard, you will see. Now, when we add a new constraint, if that constraint does not hold, okay? If there's a problem with it, if it's just cutting out the optimal solution, then it will have a negative right-hand side in your optimal table, in your previous optimal table. For example, now we have the Dakota table with the 4 constraint version, and we add a new, let's say, constraint, which is x2 is greater than or equal to 1. Normally, we are not manufacturing any x2s. x2 has a value of 0. But when you add x2 is greater than or equal to 1, you are forcing Dakota to produce at least 1 unit of x2. Okay? 1 unit of x2. Now, as you can see from the solution, x2 is 0, but the constant we are adding makes, forces it to be greater than or equal to 1. So this is going to be infeasible for this solution. Okay, we have cut down the feasible region. We have, gotten it smaller, so we have to find a new solution. Now, we just add this new constraint to the optimal table. Okay, this is just adding it normally. Okay, there is nothing else to do. Just add it normally. We already know that x2 minus e5 is equal to 1 is its standard form, so we are adding the standard form into the matrix by multiplying with -1, of course, because we need to find the e5 value. Okay, we need to see that e5 value has a coefficient of 1 to be able to be in the identity matrix. Okay, so we have -1 for x2, 1 for e5, and -1 for the right hand side. Now, this is already an optimal table, so I know that it conforms to optimality conditions. There is no problem with it. So all the values on the objective function row are already 0 or positive. So there is no need to check it once again, but you can just keep rechecking. It doesn't really matter. But this is the optimal table, so all I did was add a constraint to an optimal table. So I'll just start with the dual simplex. So there's only one negative value, which is the newly added constraint, of course. But before I start this one, I had to check, for example, if this constraint was something like x2 plus x3 is greater than 1, or x2 plus x3 is greater than 10, let's say, I would have to find the identity matrix first before starting my operations. For example, if this one, if this x3 had a value over here like 10, then I would have to multiply this row with -10 and add it here to get rid of this value, okay? We always need to see the identity matrix. In here, when we are adding x is greater than or equal to 1, we are not, disrupting the identity matrix. It stays the same with the zeros and all. But if I had in that constraint a value, for example, coefficient for the basic variables, all the basic variables in the optimal solution, then I would have to get rid of them, turn them into zeros to be able to see the identity matrix once more. So we don't need to do that here anyways. Okay, what else? Now, we have started with the dual simplex time. We are starting with it. And there's only one minus value on the right hand side, and there's only one minus value in the coefficient. So it's obvious that the pivot is going to happen for x2. x2 is going to enter the solution, and e5 will leave the solution. So let's have x2 enter the solution. To do that, we have to multiply that row by -1 and get rid of all the values above that or below, depending on where you are, but still it's above right now. So we have to get all the values above it and turn them into zeros. As you can see, this is just one iteration, and after that one iteration, we have x2 is equal to 1, and values for x3, x1, they have changed. Okay, we are now producing something else. It was 208 to x1, 0 x2, and 8 x3, and now it's 3/4, 1, 10. These are not integers. We are not looking for integer values right now. It's just linear relaxate. So we're not looking for the integer solution. So we are going to produce 3/4 of a desk, for example. The first one is a desk. So the z value, as you can see, has decreased from 280 to 275. If this is increasing for maximization after a dual simplex, you might be making a mistake there somewhere. You have to check it to make sure that it's decreasing or it's staying the same. Again, for minimization, it's the opposite way. It has to increase after a dual simplex iteration. So, 275, z has decreased, and x2 is in the solution now, and s2 has left the solution. So, e5 has left the solution, of course. Instead of e5, we have x2 in the solution right now. And as you can see in the table, the S2, S3, S1 values for coefficient haven't changed because there was nothing, let's say, affecting them in the, constraint we have entered, because it was just solely for one constraint. It was a non-basic variable anyway, so it could affect S2 and S3 like that. So they haven't changed anyway. So our dual solution hasn't changed anyways, because with the of course addition of E5, we now have a Y5 in the dual solution, if you can remember the dual part of it, but still it's almost the same. So this is what you do when you add a constraint. For example, another constraint addition. Now here we are adding minus x1 minus x2 plus e5 is equal to minus 12, or x1 plus x2 is greater than or equal to 12. Now with this addition we are actually adding a, for example, basic variable and a non-basic variable at the same time. Now in the previous one it was just one non-basic variable. Now we are adding a basic and non-basic variable together. Now when we are adding this x1 plus x2 is greater than or equal to 12, we are adding a new e5. Okay. The previous constraint is gone, by the way, don't mix them up. This is a new constraint for the same optimal solution. So when we add that constraint, now again, we have minus x1 minus x2 plus e5 is equal to minus 12, but that x1 is in the solution, so we have to get rid of that x1. So we take its row and add it to the newly, added constraint. As I said earlier, normally over here, let me just, over here we would have 1, minus 1, because we have minus 1 for this one, and minus 1 for x2, and plus 1 for e5, and minus 12 for the right-hand side. Normally this is what we have. But we cannot have a minus 1 over here, because this has to be part of the identity matrix, as this is 1 and everything else is 0. So we just add this row to the row over here. So we get rid of this minus 1, and it turns into a 1. So this is the starting table for us, and we have a negative value on the right-hand side, which means that we have to use dual simplex once again. Now in this one, we have only one minus value again, and this is for S2. Now the minus value is for S2. It used to be for X1 and X2, but after the initial iteration that gets rid of the, that helps us go back to the identity matrix, we only have a negative value in S2. If we didn't have any negative values, we would just say, okay, this is infeasible, we're done. Because we cannot apply dual simplex, and there's a right-hand side value that's negative, this is infeasible, we're done. We're going to see an example for that one soon enough, but still, here we have a negative value, minus 0.5. And it is a ratio of 20. It is really meant to be done into ratio test, because this is the only negative value anyways, but still, we're going to do the pivot for S2. And S2 will enter, and E5 will exit. So this is what happens when S2 enters and E5 exits. S2 has entered, E5 has exited. The optimality hasn't changed. We still have an optimal solution, because there are no negative values on the top side for the objective function. But the right-hand side values still have negatives. A minus 16 and a minus 32. I picked the greatest one, which is minus 32. So for the row of x3, I'm going to look for negative values. There's only one negative value, which is x2. So x2 will enter the solution, and x3 will leave the solution. And I'm going to do the pivot for x2 on x3's row, which will mean I'm just going to transform it into a value of 1. The minus 1 value will become 1, and I will get rid of all the values up and down and turn them into zeros once again, which will give me this one. Now over here, okay, we are again optimal with a negative right-hand side for z value, and two negative values, minus 20 and minus 27. Now, both minus 20 and minus 27 don't have any negative values in the coefficients or the constants on the left-hand side. No negative values there, so it's infeasible. So, what we did was add a new, let's go back, add a new constraint, which was x1 plus x2 was greater than 12. And we found out at the end that this is actually infeasible. We cannot manufacture in this, constraint, under this constraint. It's not possible. So this is what we have found. It's infeasible because there are negative right-hand side values, and there are no negative values in the left-hand side, in the constraint coefficients, in the technological coefficients. So this is infeasible. What about another type of problem? Solving a normal minimization problem. Now, when we start to solve a normal minimization problem and we're looking for this part, we are talking about just a normal minimization problem. Minimization problem with greater than or equal to signs on the constraints. Okay, this one is an easy problem. There are just two variables in the minimization, objective function. There are three variables in the constraints with two constraints. Okay, this is not that hard. We can also try to solve this by hand, probably, but still, let's say that we are trying to solve this problem. We have two options, big M, two things. The third option comes in now, the dual simplex. To be able to use dual simplex, we always say that we need to have a negative right-hand side value. So let's see if we can find a negative right-hand side value. I'll just try to write them over here. If you cannot see this, it's not that important because we will see them in the next slide in a minute, but still, let's make the operations and try to get some insight from there. We have min z is equal to x1 plus 2 x2, subject x1 minus 2 plus x3 is greater than equal to 4, and 2x1 plus x2 minus x3 is greater than equal to 6. Now, if I turn this into the table, I would have to write all those x values. I want to send them back to z, and I could write something like this one. That's x1, e1, e2. So z is 1, x1 is minus 1, x2 is minus 2, and these are all zeros with the 0 right-hand side value. Now, normally, after writing the constraints over here, I would add an artificial variable to all constraints, and those artificial variables would have, 0 values over here, and then I would get rid of those values, those x values, and plus 1 values over here because we are trying to minimize them, so they're going to be added as plus 1, and I would have to write them as minus 10 and get rid of those values using the row operations, but now I'm not doing anything like this. I don't need any artificial variables. I'm just going to write these in a minus form. So it's actually going to be minus 1 plus 2 minus 1 plus 1 0 minus 4. And the second constant is going to be 0 minus 2 minus 1 1 0 1 minus 6. Now, for this table, should be the same table in the next slide, let's see. Yes. Now, for this table, okay, it's a minimization problem. We all know that it's a minimization problem. Okay, this is the same as the slide, so you can, if you can't see the board, you can check out the slide as well. In this table, okay, we are trying to minimize it, which means that our optimal solution should contain no positive values, and this is optimal. Because there are no positive values in row 0, in our objective function row. So this is an optimal solution for us, okay? But there are negative right-hand side values over here, which means that we have to use dual simplex to be able to get rid of these negative right-hand side values. We don't need to add any artificial variables anymore. We can just use dual simplex. And to use dual simplex will mean that we are going to use enter from here, minus 6, which is the most negative right-hand side value. And then do the ratio test, as you can see in the slide, and we will get minus 1 over minus 2, which is 1 over 2, the smallest ratio for x1, which would say that x1 is going to enter the solution and e2 is going to leave the solution, and then we do the iteration. x1 enters, e2 leaves. We still have a negative right-hand side value, okay, which is for e1. So we check if we are still optimal, and we are optimal on the table, on the objective function row. So we're just going to use the dual simplex for the E1 value, enter from the right-hand side, find the ratios for only the negative coefficients in the constraint, which are minus 3 over 2 and minus 1 over 2. And we find that the least ratio, the smallest ratio belongs to x3. So x3 will enter, and E1 will leave, which will give us this table, which is the optimal table, because all top side values are negative or 0, except the right hand side value, of course, and all right hand side values for the constraints are positive. So there are no negative right hand side values left. So I don't need to do any more iterations. This is the optimal table. Now let's go back to the original one. Z was equal to 0. It grew bigger, it's got big, and it's now equal to 3, and at the end it's equal to 10 over 3, which is 3.33. It keeps getting bigger and bigger. Okay? As we make the iterations with the Dual Simplex, we are getting worse and worse values for our solution, optimal solution. But this is something we're expecting. Okay, this is another part of the Dual Simplex method. Now, what about making a wrong iteration? Okay, due to miscalculated ratio. This happens all the time. I had already told about this one to you for the midterm, I guess. It might happen. All you have to do is just backtrack and try to correct it, or you can use Dual Simplex to deal with it. For example, this is the Dakota example with the last row taken out. We don't need that last row anyways. And in this point, the ratio, this is not an optimal solution yet. So we are trying to make an iteration. This is the last iteration before the optimal solution, if I'm not wrong. So we are trying to enter from x3, which is a value of -5. And we say that we need to find the ratio. And do the ratio test, 4 over 0.5 becomes 18 instead of 8. We are writing it wrong. It happens. So we have picked a bigger ratio, which is 16. It should have been 8 and 16, and 8 would be picked, the smallest ratio. But instead of 8, we have written 18 by mistake. So we are picking 16. What happens now? Let's see what happens when we pick the greater ratio. We make the iteration. We find a z value of 320. Okay, the optimal solution had a z value of 280. I don't know if you remember it, but still. Instead of 280, we have found 320, a bigger solution. But we have a negative right-hand side value, -4 for S2. So we have made a mistake. Okay, in normal simplex, we should have found something like this, but we have found a negative right-hand side value. Now, this can happen in two different ways. We are making the calculation wrong for S2, and we are making the calculation for the right-hand side, or we have picked the wrong ratio. Now, that might happen. Assuming we have picked the wrong ratio, we can just go back to our calculation beforehand and find the new ratio and then do the simplex from there, or we can just backtrack using Dual Simplex over here. It might happen as well. Now, what happens if I use Dual Simplex? I have a value of -4 for S2. So, what I need to do is just take that row, find any negative values, and find the ratios. So, as you can see, for S2, there are 3 different negative values. X1 is -2, X2 is -2.5, and S3 is -3. If I take the ratios, 20 over -2, 30 over -2.5, and 40 over -3, again, the absolute values of ratios, of course, I will get 10, 12, and 13.33. So, from here, I know that I'm going to pick X1. X1 is going to enter the solution, and S2 is going to leave. So, my pivot point is going to be -2. If I take that pivot, I will get this, the top side table. And in this table, as you can see, I have reached the optimal solution. Okay, we have a z value of 280. It had to be 280, it should be the same. And the values are the same, 208. X1 is 2, X2 is 0, and X3 is 8. So the solution is the same. And in the bottom table, you can see the solution from the book, the actual solution. There's a difference, a small difference. Row 2 and 3 are reversed. They have changed places. That's it. There is no other difference there. It's the same thing. All the coefficients are the same. They have to be the same. But only row 3 and 3 have changed places. And that's okay. It's just a simple, row change. It doesn't change the answer. It's the same thing anyway. So, as you can see, by comparing these two, we can see that, okay, after making a mistake, Dual Simplex just helps us revert back to the right place. And it has done it in one iteration as well. It might have taken longer. It might even get us a shorter route. There's a possibility, however small, but making a mistake and letting Dual Simplex correct it might make the number of iterations maybe smaller, because when you take bigger steps, you get closer to your objective function, the optimal solution, faster. For example, think about it like this. Let's assume that there are 5 points that, 5 points that can be the optimal solution, but this is actually not infeasible region. And these are all, neighbors. So normally, with smaller ratio, if it said that you would have to go like this one over here to find the optimal solution, you would need to make 3 iterations. But for example, if you made a mistake and jumped over here, and then came back over here with dual simplex, you could have found that one 2 iterations. That might happen. That doesn't have to happen, of course, but might happen. So sometimes making a mistake like this might be useful if you know how to backtrack with dual simplex. Of course, don't try that ever, but still, it's something that can be done anyways. So this is dual simplex. Okay, with dual simplex, again, this has nothing to do with duality. Okay, actually, it has something to do with duality, but don't mix them together. Okay, finding a dual has nothing to do with dual simplex. That happens every year. In the exam, for example, in the midterm or the final, when I say use dual simplex to find a solution, some of the students just take the dual of the primal model and use normal simplex to find the solution. And I'm like, what? No, it's not dual simplex. Okay, dual simplex should not be confused with duality. Okay, don't confuse them. They have the same name, okay, dual, they both have dual in it, but dual simplex is how you get rid of negative right-hand side values. Of course, there is a simulator or there is a connection between them, yes, but you don't need to, focus on that connection to be able to use them. Okay, there are 2 different algorithms, entities, whatever you want to call them. All right, so dual simplex is used to get rid of right-hand side values, negative right-hand side values in an objective function that is optimal. Okay, when you have an optimal objective function and negative right-hand side values, you have to check if you can use dual simplex to get rid of them. If you cannot, they're infeasible. If you can, okay, good for you. So let's take a break and be right back after